question comes out of 4.4 applied max-min problems. So a different kind of setup here. We're asked to find the points on the parabola y equals 8 minus x squared that are closest to this particular point. So you might want a little sketch what that parabola looks like. 1, 2, 3, 4, 5, 6, 7, 8. We have ourselves a parabola faces down, looks like that. The point 0, 5 is here. And we're looking for, even visually, some kind of point that's roughly here and here. It looks like there would be two that would be the same distance away, but let's just call the point xy. We know this point is 0, 5. Distance between 2 points is equal to the difference in x coordinates squared plus the difference in y coordinates squared, and then square root. Basically the Pythagoras situation. If you can zoom in on this tiny little distance here, we're saying, well, this distance squared plus this distance squared would equal that distance squared. So in this case, the distance between our point x, y, is going to be x minus 0 squared plus y minus 5 squared. To say, okay, any point x, y, and the point 0, 5. Now, I can make that look a little bit better by saying, well, x minus 0 is x squared, and the fact that that's our objective. Our constraint is the fact that the point xy has to be on this parabola, meaning that y equals 8 minus x squared. And that's key because now I can say b equals the square root of x squared plus, instead of having y minus 5 squared here, I'm going to have 8 minus x squared minus 5 squared. Now, before I start diving in and taking derivatives, I can make that look a little bit neater and tidier to say, okay, let's say this is 3 minus x squared squared, so the square root of x squared plus 9 minus 6x squared plus x to the 4. So put it all together, I've got distance equals square root of x to the 4 minus 5x squared plus 9. Now that is our objective. We're trying to find the minimum, so I need to say, well, the derivative of that, dt by dx, equals 1/2 that to the negative 1/2 x to the 4 minus 5x squared plus 9 times the derivative of the inside, 4x cubed minus 10x. Make it look, again, a little bit better by saying, okay, well, multiply the half in there, I'm going to have 2x cubed minus 5x over the square root of x to the 4 minus 5x squared plus 9. I want to know when that equals 0. So as much as that denominator looks terrible, I don't really have to do anything with it, because I'm really just looking for, what, if I multiply both sides by that square root term, I'm really just looking for when does 2x cubed minus 5x equal 0. So factor it the best I can. And I say, well, either at x equals 0 or 2x squared minus 5 equals 0. So x squared equals 5 over 2. So x equals plus or minus the square root of that. It's plus or minus the square root of 2.5, or 5 over 2. If you look at those values to see what are max, what are min, 0, square root of 5 over 2, negative square root of 5 over 2, you'll actually find that you have a minimum there and a maximum at 0 and a minimum at root 5 over 2. So you do have two min points that are as close as possible to the point 0, 5, but you have that one at 0, 8 that's actually a local maximum. So I won't bother finding that since we're asked to find the closest ones. So to find the actual points, then I say, well, if x equals negative square root of 5 over 2, y equals 8 minus x squared, so 8 minus that squared is going to be 5.5. So I have a point that's at that coordinate, and the same thing for the positive square root of 5 over 2, y also equals 5.5. So I have 2 points. You could make them look a little nicer by rationalizing and whatever, but basically you have the idea. You have 2 coordinates that are giving you a minimum distance to that parabola.